All right, welcome to this explainer. Let's just dive right in, shall we? Today, we are going to demystify the absolute reigning champions of spreadsheet data. You hear a ton about neural networks and deep learning these days, it's everywhere. But we're going to prove exactly why those super trendy models aren't always the magic bullet for your data. When you put these models head to head for standard tabular data, tree-based models honestly just crush deep learning. We're talking about training times in minutes rather than hours. They give you full transparency instead of acting like a total black box, and they naturally handle mixed data types without a fuss. Now, sure, neural networks absolutely win for unstructured stuff like images and text, but for flat tables, trees are the default for sure. Okay, so here's our roadmap for unpacking all of this today. We're going to hit the underdog rivalry, anatomy of a tree, splitting math, stopping conditions, and wrap it all up with building the forest. Let's get to it. Starting with section 1, the underdog rivalry. We're kicking off with a pretty bold claim here. When it comes to the data most businesses actually use day in and day out, those older, simpler tree models, they are the true heavyweights, especially when you're dealing with smaller datasets, specifically anything under 10,000 rows. Trees perform incredibly well here. This is a scenario where neural networks will almost always overfit, meaning they basically just memorize the training data instead of actually learning the underlying patterns. Trees, on the other hand, are highly resistant to that when you set them up right. Moving right along to section 2, anatomy of a tree. If we step away from all the fancy data science buzzwords for a second, a decision tree is really just a hyperfast game of 20 questions. It systematically partitions the feature space into rectangular regions using a sequence of simple yes or no questions. So every internal node tests a single feature against a threshold, and then it routes the data down specific branches based on the answer. It keeps doing this until it hits a leaf node at the very bottom, and that leaf node is what makes your final prediction. The beauty of this? You can trace the exact path and see exactly why a specific prediction was made. Now, under the hood, this uses what's called a top-down greedy algorithm, and man, it is unbelievably thorough. It systematically tests every single option to find the absolute best separation for the data at that exact moment. It sorts the samples, tries every midpoint between consecutive distinct values as a threshold, computes the information gain, and picks the absolute best one before moving on to the children nodes. It literally checks everything. Which brings us to the math behind it in section 3, splitting math. So how exactly does the algorithm define what the quote-unquote best separation is? Well, first up, we have Gini impurity. This is simply the probability of misclassifying a random sample at a node. We obviously want our child nodes to be as pure as possible, right? We want them mostly containing one class. Gini impurity measures how mixed that node is. If it's totally pure, the score is 0. If it's a perfectly even 50-50 split in a binary scenario, it hits the maximum impurity of 0.5. So a lower score is exactly what we're hunting for here. Alternatively, you can borrow a cool concept from information theory called entropy. Entropy measures the actual information content, or the disorder, in a node. Just like with Gini, reaching 0 means you've got a perfectly pure node, while a 1.0 means maximum uncertainty for a binary split. Honestly, in most real-world cases, Gini and entropy are going to give you nearly identical results. And that leads us to the core mechanic driving all of this: information gain. This is just the reduction in impurity, again, whether you're using entropy or Gini, right after a split happens. So the big takeaway here is that at every single step, the tree is greedily hunting for the specific feature and threshold that will maximize this information gain. All right, section 4, stopping conditions. Here's the catch, though. Trees are incredibly greedy. Like, if you just leave them alone, they will perfectly memorize your training data and just completely bomb when you put them in the real world. To fix that overfitting, we have two main strategies. Pre-pruning stops the tree growth early by setting hard rules, like a maximum depth or a minimum number of samples. It's much simpler and way faster. Post-pruning, on the other hand, lets the full tree grow out first, and then it goes back and trims away subtrees that don't actually improve validation performance. It takes a bit longer, but it often gives you better overall results because it doesn't prematurely stop splits that could have been super useful further down the line. Oh, actually, real quick side note here. Everything we've talked about so far is for categories, but if you're predicting a continuous number, let's say a house price, the tree works a little differently. The leaf predicts the mean of the target values in that leaf, and instead of looking at information gain, it picks splits based on variance reduction, basically finding the split that shrinks the target variance the absolute most. Finally, let's hit section 5, building the forest.
So a single decision tree actually has pretty high variance. Even tiny little shifts in your training data can produce a completely different tree. It's kind of fragile. We fix this by turning a bunch of mediocre individual trees into an absolute powerhouse, the random forest. By leveraging the wisdom of the crowd, we average out many decorrelated trees, which drops the variance without jacking up the bias. And we pull this off using two key sources of randomness: bagging and feature randomization. Let's look at how they work. First up is bagging, which is short for bootstrap aggregating. This guarantees that each tree is trained on a totally different bootstrap sample. Now, a bootstrap sample is just a random sample drawn with replacement from the original dataset. Because you're putting things back and getting duplicates, there's actually a fun math quirk here. Only about 63% of the original samples actually make it into each individual tree. Combine that with feature randomization, where at each split only a random subset of features is even considered, and you keep the trees incredibly diverse. Now, one of the coolest things about random forests is they naturally reveal which features actually matter the most. But you do have to make a choice on how to measure that. You can use mean decrease in impurity, or MDI. It's super fast, it's computed right during training, but it has a known bias toward features with lots of unique values. Or you can use permutation importance. This literally shuffles a feature's values around to measure exactly how much the model's accuracy drops. It is slower, for sure, but it is way more reliable, especially if your data is a bit noisy.
So let's bring this all together. Deep learning models and transformers, yeah, they grab all the flashy headlines. But for that flat Excel spreadsheet you're opening up every single day, the random forest remains the undisputed king of the real world. So it really leaves you with one question. Which one is actually running your business today?